Hey, hi everyone. So, sorry, there was like couple of days I didn't study, which is not nice. Preferably, we'll try to meet every day. Okay, now what we have looked at is neural networks, how the multi-layer neural networks is formed, how each layer contributes to the next layer, and we understood saying the neurons in each layer in turn help in giving us a small part of the big line, and those smaller parts are actually as it goes through multiple layers, what happens is we adjust the weights in a way that the small part of the line which is derived by a sequence of neurons is actually aligned to our data pattern of the data. So all these small lines will actually get adjusted to the pattern that we frame, which is actually driven by adjusting the weights, and the weights are adjusted through back propagation. Um, Weights are adjusted through the same gradient descent formula, that is W is equal to W minus lambda by 2 into derivative of loss by W. But in back propagation, what happens is because the W in the layer get the derivative of W in the first layer, basing on the loss of the final output, we use for calculating it, we use back propagation. That's all. Okay, that we have seen on how chain rule of derivatives and stuff, how it works to derive the value of derivatives and stuff. Um, we looked at activation function. We looked at regularization techniques. We looked at uh, optimizers like gradient descent and other optimizers. Um, Adam optimizer, gradient descent, and then uh, RMS prop, and all that. And we left out last topic in neural networks that we thought of covering is hyperparameter tuning, because in neural networks, as we discussed, there are a lot of things where we had choice to make, right? For example, number of layers, number of neurons in each layer. Uh, I wouldn't say number of inputs and number of outputs, because you know what X is, what Y is, so you would classify X and Y accordingly. Um, the activation function that you use for within these neurons, if you use regularization terms, then regularization terms has these factors that we use to multiply in L1 and L2. You remember lambda W1 sum of W1 and lambda sum of W2 square are the formulas, right? So you have one is sure what you call it, one is lambda, another one is sigma, something like that. Okay, there are two variables with which we multiply the sum of W or sum of W squares for regularization. So those two terms are there, and when you do gradient descent, and when you calculate the W values using back propagation, we will use the learning rate. So that's also hyperparameter. Mm, what else is there? Let me let me ask this thing ChatGPT, and then we'll go from there. This is oh, first one is still nice. each of them. Okay, let's see. Most of them are what we have discussed already. Number of hidden layers. That means so here, as we said, we can increase the layers, right? So the number of hidden layers that we need to keep. I mean, as the number of hidden layers increase, the complexity of neural network increases. As the complexity of neural networks increases, the adaptation to pattern increases. But at the same time, the compute and memory utilization, all of this will also increase at the same time. So be um, we should be picking up the numbers of these layers which are meaningful, as per the data that is given, as per the accuracy expectations of neural networks, and all those elements we should pick it up. Okay, that's hidden layer. Number of hidden layers determines the depth of the neural network. Each hidden layer extracts and learns features from the input data. Yeah. The way what happens is, let's say if you give an image to a neural network, the understanding is the neural networks, the pattern that has been observed is it learns a part of it. Like you give a human image, right? Human image. Then when you train a neural network through multiple layers, what we understand is it will learn a specific part in each of them, in each of the layers, and and those specific parts that it learns, saying, okay, so for example, certain neurons will help in finding out that this image has hair. Okay, so the hair's pattern, it will, as you fine tune it, the hair's pattern, so within an image anywhere, if there is hair, after learning on multiple images, if there is hair, this particular neuron will detect it. By the time it reaches the outer layer, or outer layer minus one, and output minus one, hidden layer, it will know that, it will flag off saying this image has hair. Similarly, some flow, by the time it reaches the output layer, it is sure that it has a nose. Like that, it will figure out small pieces within the image that we have given in, and those small pieces could put together, as we see another day, right? Like, so if you take, this is one feature, this is little finger is one feature, another finger. Like each finger might be taken as one feature, and it will remember saying, I, when you give an unknown data, something like this, it will actually try to find out each of this part of it, and it will figure out if, okay, this side is there. So if the side is there, it'll that will detect this side, or it will say, if, because the size is partially there, it will say that this size is partially there, kind of stuff. So um, within neural networks, we are distributing the pattern that we observed is that it usually distributes the thing. Um, I know this will unnecessarily taking more time here, but neural networks feature distribution and detection. here somewhere the image will be there where the image will show how for a given input of specific image. Where is it? Image recognition outputs is the point is on output distribution of particular image. It's okay. Go to the playground. Actually, we didn't run this. If we run it, we can see how it would adopt. But instead of this data, show test data, discretize output, we can't use a problem, classification regression problem. We can't use an image data or something. Oh, here we can have. If you see, this is not even taking anything on orange, it is actually taking everything on blue only. I think it is stuck, it is there only. It is not going beyond, or it's very slow. So now if we increase the learning rate, yeah, it is jumping out. So reset 0.1. See, these two are doing the same thing, like this, like this. like this, and then this is only doing this, and this. Output is this and this. These two are only blue shades that are coming in. Oh, this is blue shade. This is orange shade. Okay, orange. It's showing us blue here. Actually, is orange. Mhm. Now this didn't work. So now we need to figure out how do we should we add more layers or should we do one thing? How do we decide how many layers should we add? These are all something which we should learn today. There are some metrics I forgot actually on. They're not even metrics. They're more like suggestions on what is the how do you pick the distribution of the neurons and stuff. We will learn today all those things. Okay, let's try this. Now I added more hidden. I added an additional hidden layer, and I also added mm, this thing. I'll see if outputs if we go with 1 and 2, what will happen. Oh, what is this line? Oh, loss. Okay, it's decreasing, but it is fluctuating up and down. Loss is going higher as the number of iterations are moving up. It is almost close except for this piece. Part of it is almost close. And from here, see the test loss and training loss, they have become straight line. So that means it is not working anymore. There, that's the best picture possible with this particular classification, and it looks almost good, right? So, but we'll look at what's happening with each of these stages. This has picked up. Why does it say orange color? Click anywhere to edit. Bias is minus 1.8. Okay. Bias 6 dot. Oh, okay. Like the bias term that is there. We can edit it if you require, it seems. So most everything is being L1, L2 regularization rate. We didn't use any regularization, by the way, which is okay. Ratio of training to test data, 50%. So, okay, let's put it this way, 60% noise. Okay, we'll learn about noise also. Batch size 11. We don't know the data set size also, but we are following it, but it's okay. So we reset it, right? The loss actually suddenly, both the losses increased. It went down for some time and then it increased way up. I I think it jumped the optimal point is somewhere here below. It jumped it because of the higher learning rate. So we should decrease the learning rate. Okay, let's go with the optimal. Usually learning rate, we start off with our starting point is 0.01 and then we'll move it up and down basing on the need kind of stuff. Okay, let's see how it goes now. Okay, it's smooth. The test loss is going down significantly. The training loss is still up. Okay, both of them are going down. Very nice. Yeah. I think they're almost straight line. Maybe that's the minimal loss or few iterations. These two orange boxes may touch each other, I guess. Oh, they already did. I think this is I think this is the minimal loss that we could see because see almost everything in orange. I don't know why training set loss is 0.055. Okay, it's minimal. Maybe 1 point or something is there, but if you see for naked eye, almost everything is there. Maybe somewhere here, if there is an overlap, it might have there, but everything is here. So this is definitely overfitting, but let's see how it is doing it. First layer, second layer. I think in the whole set, this piece of orange is picked up by this one. Okay, good. Now, second piece of orange is picked up by this. So it's actually classifying by orange, not by blue. Both of them are picking up pieces of orange. So this is so if it is divided the whole data into two segregations, and the first neuron is helping in picking up the first one, and second one is now what happens if we pick up more neurons here, then it will divide into more smaller parts. As I said, in the image classification, it divides all parts. So what happens? Another image comes in, another data comes in. It if it is part of this neuron will help in detecting it. If it's part of this neuron will like that it would go. But let's run the training once again. You can actually see the test loss and training loss here, and because we have more output neurons, I think it's working faster. Let's see which output neuron will actually pick up which part of the output. Now these two are overlapping with each other. And I should have noted the epochs. The epochs previously are actually good. This is taking more time and it's going up and down. The previous one is more stable and it's going down continuously. See, the test loss is mounting, so this going to convergence is harder. So having three is actually the output is creating more problem. Okay, let's stop it because it's not converging that soon. Let's reduce it and see if we have one, what happens. I think one will not work because a single neuron can't take all this shape. Yeah, it's almost like we're putting a one single equation, right? So yeah, it will come like that, single neuron. But let's see what happens. Oh, hmm. It's, It's adapting actually. You see this piece, it shows it is struggling to pick up this piece part of it because one in single thing it's trying to put the whole neuron and it is not able to do it. So that's the reason. Okay, let's pick up two. And two anyways we have seen it is working out well. Um, one here. Instead of ReLU activation, let's say if we take sigmoid, what will happen? And we should use the same one. So let's use the same neuron. Go. Oh, ReLU was much smoother. Sigmoid is not. Sigmoid is flat now itself. Yo, because sigmoid is 0, 1, it's more 0, 1s. So this problem statement will not be. Sigmoid is not a good choice. Okay. Linear sigmoid ReLU will not. ReLU tan H. I'm not sure how it would work. Let's go. Test loss is going down. Training loss is. Then it is low. It's going good. This trying to assume that this is blue or because of this it is taking its shape, but yeah, slowly orange has pushed it out. Whole blue thing. This gap it is trying to see if it is blue. Okay. Mm-hmm. It's struggling. Oh, fluctuation. So 0.192 is the training loss, 0.21, but whereas ReLU when we went, it went to 0.055. And from now there are too many iterations and it is actually started fluctuating the loss. This whole loss is not steady. So we've crossed the boundary where it would really fit in. And it's just flickering there itself, not going down any further. Okay. Going back on ReLU, just repeating on what we have learned. See, ReLU, the test loss is low, the training loss is high, initially at least. Okay, that steep is low for less number of iterations. You see, 700, less than 1,000, and we have adopted to the rate of the loss is 0.033 and stuff. It's very good. Those are all waste. See, optimal point is here. So now it's keep going and there is fluctuation of data, but we're already there. So if you refresh and we notice somewhere, let's stop at 500 or so. Again, the behavior is a little different here. Interesting. Now it's struggling. Previously below 1500 or so itself, it has got to a good state. Now even after very slow. I think every time I do a refresh, the bias terms something that is changing. So the behavior is different. Mm, yeah, see, this time at 400 itself, it's almost, not almost, it's there, except these 2 points or something like that. 0.078. That's 0.055 was the best score we've taken last time. And now it's very good. So it's now getting fluctuated. 500 or so. Yeah, see, it became straight line. That means this can't be further improved. This point is outside. Other than that, thing else. So we pause it. This is picking up the whole blue. This is picking up this part of the blue. This part of the blue. And this part of the blue. Hmm, interesting. What happens if we increase the batch size? Make it 18. Let's go. Hmm. Mm-hmm. No, not really. Converge, but it's taking more number of epochs. That's all. Yeah, yeah. Mm. Oh, it got to a good distance. Suddenly it has spiked. So till here it is good, and after that it again went to a spike. Again it is going down, kind of stuff. That's interesting and learning. Okay, fine. So this is going good. So we'll go back to this. So number of hidden layers, you have seen how it impacts the overall performance. Number of neurons per layer. Also, have seen how it impacts the performance. Activation functions, we have seen how we change different activation functions and what it means if you go for logistic, I mean sigmoid, relu, tanh, linear, and all that stuff. Um, Softmax, learning rate, control the size of the step, but learning rate coming with regularization, we didn't use regularization. We're not doing experiments, so, but when you do regularization here, like let's say if you keep L1 regularization and then you make a choice, regularization rate. Regularization rate and learning rate is the same. No, 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 no. See, declaration rate is lambda or sigmoid or something like that in multiplied by W1, W2. Learning rate is, sorry, learning rate is W1 minus learning rate by M into the derivative, right? That's learning rate. Impacts the overall steps that you're taking with respect to W. That will impact learning rate a lot. 0.03 is optimal, 0.01 is very slow, 0.01 is too fast. See, it went very fast, but after reaching certain state, it actually slowed down. Again, going down, 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 0.10. Yep. So 0.1 also is working fine. and it is brought down in pretty decent number 0.023. That's almost like the best till now 0.023. Learning rate increasing learning rate worked actually. But what if you go to 0.3? See the test loss and training loss. So the local optimal level where it is supposed to go, it is skipped that and then it went somewhere else and it is traveling there. So 0.3 is a bad choice. 0.1 is good. You can see that descent is pretty good. That means these are all areas where it is where we are playing with unnecessary um, parameters, and those we have avoided pretty quickly, and we minimize the loss. Every time you run, it has a different behavior. I think mostly because of when you refresh or something like that, it is changing the initial weights or bias terms, something like that. So, oh, it's not even converging now. That's very bad. It is converging, but it's going very slow. So this all piece is left out. Or this all piece is not even considered. See, everything is left out. Whole thing. That's interesting. Struggling. That's mostly because of the L1 regularization. If the L1 regularization is not there, if I make it none and rerun it, yeah, see, because the regularization is not there, it is picking up 300 epochs and it's already in shape, almost in shape. Yeah, loss is already 0.055. Only thing it's not going below. You go high, yeah, it's just starting it. Mm, it's not going towards convergence or this is minimal loss 0.029. But 0.023 is with the minimum loss that we have seen, but 0.029. It's because of that gap thing. But none, whereas with the L2, what happens? One is W, L2 is W square. So W square will actually regularize it more. And the learning, the overall learning and will be slower because you're giving more, you're adding more to the loss. It's struggling because the remaining part of it, it is regularizing from adapting to it. So it is only adapting small piece of it. Only if you see both of them are targeting only here. They're not going beyond this piece. That's because regularization. And L1 is both of them are inside previously. L1, let's see. L1 is most probably outside. Yeah, outside. If you put together L1 and L2 together, it is perfect. Oh, actually, matter of fact, L1 regularization is still supporting and you're getting to 0.021, 0.020, which is okay. Again, with every iteration, it is behavior is different. Okay, going back on the activation functions, learning rate, batch size determines the number of samples processed before updating the model's parameter. Larger sizes may result in faster convergence but require more memory. Okay, let's observe that pattern also. Batch size 18. Let's say larger batch size. Start. Yo. Oh, you see the already loss is close to training loss is 100. But they are struggling. 0.143. Yeah, from here it is struggling. But it said the convert batch size, if it is increased, the convergence will be faster. I think. Oh, okay, okay. 1 second. Let me remove the declaration and see. Okay, struggle, 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 struggle. Okay, too much of struggle. Okay, loss is already 0.0. It's going below, but it's fluctuating at the same time. It's left out this piece. Even the regularization is not there, it's left out this piece. I don't know why. Full match 30. Let's see what happens. Number of iterations. Yo, 300 iterations and it's already below 100. See, the iterations are here and the loss is here, training loss is here. It's going up again. Bigger batch size, I think it's going. The actual results, if you look at it, the smaller batch size has better results, better accuracy. That is 0.058. It's not going below that when I say it. It's only going there 0.02. It's going down 0.27. Ideally, I should see both of them 0.019. I think this is really good. Let's see to optimize anything below. I don't think practically has optimized the best possible, I guess. See, it has become straight lines. So the loss is minimal. See, both 50, because we have made 50%, 50%, both the graphs are same, almost the same. 800 and it's at 0.05. Now it's become stable, except these points. I think almost the orange points in orange zone. I think it will not reduce. Let's see what happens now. 70% train data and 30% test data. The training loss should go faster. Test loss should be higher. And they're readily going in similar pace because the test data set is 30% and higher. It is not coming down. Previously, if you've seen, the test data was going down, training data is still up, but now it's the other way. Few of the neurons, if they're not picking up this area, see, this whole, yeah, this one is there. This one is also here. This is, it comes here. These are the two things that you're picking it up. The lower this one is not impacting it. Like, let's say 0.12. Does it affect it runtime or how is it? I don't think it'll affect it runtime. That's very difficult. But the utilization, even though we don't add it, it's kicking in, right? Somehow. The test data is very low. The training data is being high. The loss of training data is very high. It's not coming down. It doesn't have enough data to train. That's the problem. Now it can't generalize that. Very difficult because it has very 40% of the data and 60% of data it doesn't know. So predicting the data for 60% is impossible. It doesn't even have the whole curves that are required kind of stuff. If you see, all of them are routing to certain part of the data only. Mhm. Okay, so batch size we have seen, epochs we have seen, basing on the number of epochs. One epoch represents a complete pass through the entire dataset during the training. Specifies the number of times the entire dataset is processed during training. Means entire dataset in sense entire um, training dataset. I mean test dataset can also be considered, but test dataset is more to look at how the loss is happening. Optimizers. Adam SGD in the diagram that we have, we don't have a choice of picking up optimizer. I think so. He's picking up Adam is what I'm thinking. This is the output from one neuron. The output mixed with varying weights, thickness of the lines. So test data, discrete output. Okay. Optimizers are not given, but optimizers you already we have studied Adam, SGB, RMS prop, and etc. Control how the models parameters are updated during training. There's one hyperparameter that is example momentum decay rates. Yeah. Okay. Declaration techniques such as L1 and L2 dropout and batch normalization help prevent overfitting by penalizing the larger weights and reducing noise during training. Dropout rate specifies the probability that a neuron will be randomly dropped out during training. More robust representation. Okay, weight initialization. Determine how the initial weights are assigned. Like, what is the initial weights of the W? Assigned to the network's parameters. Proper initialization. Learning rate schedule specifies how the learning rate changes over time during training, and techniques such as learning rate decay, warm restarts, and adaptive learning rates can be used. Means instead of going with standard learning rate, we go with adaptive learning rate. And adaptive learning rate is itself is the Adam. Adaptive learning rate and with optimization, not optimization. I think the gradient descent, all those corresponding is either batch or learning rate. This adaptive learning rate is a combination of both adaptive learning rate change and also Adam is and also adding batches, both batch of size some value and then both combination is so gradient clipping limits the magnitude of gradients during training to prevent exploding gradients. As stabilized training, especially in deep networks. And recurrent neural networks, okay. Clipping. How to pick initial values of these. Start with a small number of layers and then gradually increase complexity. You know, problem analysis. Architect. Oh, sorry. I try to use ReLU or its variants, like as example, Leaky ReLU, ELU, as default choices for hidden layers. Okay, use softmax for output layers in multi-class classification tasks, and sigmoid for binary classification tasks. Okay, multi-class classification softmax output layer alone. The internal layer is the best is ReLU. See, Adam optimizer is the best. Active ReLU is the best. Learning rate. The learning rate in the range of 0.001 to 0.01 as a general rule of thumb. The loss is diverging. Increase the learning rate. That size should be basing on the compute that you have. Decrease the batch size, lower compute, increase the batch size, higher compute. Okay, powers of 2. 128 GPU. Sample 50 and monitor the training loss, validation loss. Optimize. Adam is a popular choice of optimization due to its adaptive learning rate properties. Start with Adam and experiment with other optimizers. Example SGD, momentum, RMS prop, performance and validation set. Okay, but Adam is the best. Regular parameter 0.001 as a default choice to prevent overfitting. Okay, weight initialization. Use random initialization. Small values done from a normal distribution. Example mean equal to 0, 0.1, or uniform distribution. Example minus 0.1 to 0.1. Okay. Learning rate schedule start with a constant learning rate and exponent learning rate schedules. Example. So like cosine gradient clipping. Set the threshold values 1 to clip the gradients and to prevent them from becoming too large. Okay. Yeah, 3%. It's, I think I'm gonna die. We'll search on. No. So this is not the one. Um, it will also give Python code to make to or to compare parameters and make a choice of the best. To compare different hyperparameters and the best combination. See, best combination using Python, you can use techniques such as grid search, random search, and cross validation. Using scikit-learn for a simple neural network classification task. So what they do is they create a param grid with the hidden layer sizes like 50 hidden layers, 100 layer layers. Activation function relevant and solver, Adam and CD, running a constant and adaptive. Initial classifier, perform grid search with cross validation. Best parameters, grid search underscore dot best parameters. When you show grid search, what happens is that they'll go with all combinations possible. ABC with, and then they pick up different combinations of those, and they make a choice of which one is working fine. Hypermode using grid search CV. Okay. 16 minutes, 9 minutes, 10 minutes from. Okay. Didn't get much, but okay, fine. I'll end the video here. It's already too long, and we need to start off with other things we do. I'm not sure if my voice is audible today because I was speaking very low. That's okay. Fine.